phenomenon where fluorescent light requires a static shock to start can be attributed to several factors. Firstly, when waving a hand near the lamp, a static electricity discharge occurs. This discharge provides a voltage surge that can trigger the starting circuit in the fluorescent fixture, causing the lamp to ignite. Secondly, the gauge of the wiring plays a critical role in supplying adequate power. The use of 18 AWG wires in the flexible cable might be insufficient for reliably starting the fluorescent fixture. Fluorescent lamps need a high initial current surge to ignite. The small wire size might not be able to effectively deliver this current. There are other possible causes to consider as well, one being loose electrical connections. Inspect all connections meticulously. This includes connections between the flexible cable and the fluorescent fixture, and also connections between the fixture and the main power source. Loose connections introduce increased resistance, and this can cause intermittent starting problems. Also, consider the ballast, which regulates the current flow to the lamp. Over time, ballasts deteriorate, which makes them less efficient, potentially affecting the fixture's ability to start the lamp. Dirty lamp contacts can also prevent proper electrical contact. The contacts on the lamp ends can become dirty or corroded, preventing proper electrical contact. You can clean the contacts with a cotton swab dipped in rubbing alcohol. To correct the underlying problem, it is recommended to replace the existing flexible cable with a proper cable that is sized appropriately for the load. Increasing the cable size to 14 AWG or even larger will ensure sufficient power delivery to the fluorescent fixture. When selecting the appropriate wire gauge, consult the National Electrical Code, specifically NEC Table 310.15b16, to determine the ampacity of conductors based on their insulation type and temperature rating. This table provides guidance on the allowable ampacities for various wire gauges in different conditions. For example, for a typical installation with type THHN or THHW insulation, a 14 AWG copper conductor has an ampacity of 15 amps, while a 12 AWG conductor has an ampacity of 20 amps, and a 10 AWG conductor has an ampacity of 30 amps. Always choose a wire gauge with an ampacity that meets or exceeds the circuit's overcurrent protection. When replacing the cable, ensure that all connections are made properly and are secure. Use appropriate wire connectors rated for the wire size and application, and tighten them according to the manufacturer's instructions. A loose connection can create resistance, which leads to heat buildup, voltage drop, and potential fire hazards. After replacing the cable, test the fixture to ensure that it starts reliably without the need for a static electricity discharge. If the problem persists, further investigation into the ballast and lamp contacts is necessary. A faulty ballast may need replacement, and cleaning the lamp contacts can improve electrical conductivity. To further elaborate on the insufficient power issue, it's essential to understand the electrical characteristics of fluorescent lamps and the role of the ballast. Fluorescent lamps require a higher voltage to initiate the arc that produces light. The ballast provides this initial high voltage and then regulates the current to maintain a stable light output. If the wiring is undersized, it can create a voltage drop, reducing the voltage available at the fixture. This voltage drop can prevent the ballast from providing the necessary starting voltage, leading to the need for an external trigger, such as a static electricity discharge. The voltage drop can be calculated using Ohm's law, which states that voltage equals current times resistance. The resistance of the wire depends on its length, gauge, and material. For example, the resistance of 18 AWG copper wire is approximately 6.385 ohms per 1000 feet at 20 degrees Celsius. If the wire run is long, the voltage drop can be significant, especially under high current conditions. Using a larger wire gauge reduces the resistance and minimizes the voltage drop, ensuring that the ballast receives adequate voltage to start the lamp. When checking the connections, pay close attention to the wire nuts or other connectors used to join the wires. Ensure that the wires are properly stripped, twisted together, and securely fastened by the connector. Loose connections can oxidize over time, increasing resistance and causing intermittent problems. It may be necessary to replace the connectors if they are old or corroded. Regarding the ballasts, There are different types of ballasts, including magnetic and electronic ballasts. Magnetic ballasts are older and less efficient, while electronic ballasts are more modern and energy efficient. Electronic ballasts also tend to provide better starting performance. If the fixture has a magnetic ballast, consider upgrading to an electronic ballast to improve starting reliability and energy efficiency. The lamp contacts on the lamp holders can also be a source of starting problems. Over time, the contacts can become dirty, corroded, or bent, preventing proper electrical contact with the lamp pins. Clean the contacts with a cotton swab dipped in rubbing alcohol or a contact cleaner specifically designed for electrical connections. Ensure that the lamp pins are also clean and free of corrosion. If the lamp holders are damaged or worn, they should be replaced to ensure proper electrical contact. In addition to these specific issues, it's also important to consider the overall condition of the electrical circuit. Check the voltage at the circuit breaker to ensure that it is within the acceptable range. Low voltage can also contribute to starting problems with fluorescent lamps. If the voltage is consistently low, it may be necessary to consult with a qualified electrician to investigate the cause and make necessary repairs. When working with electrical circuits, always follow proper safety precautions. Turn off the power to the circuit before performing any work, and use appropriate personal protective equipment such as insulated gloves and safety glasses. If you are not comfortable working with electricity, it is best to consult with a qualified electrician to avoid the risk of electric shock or fire. Also, when selecting replacement cables and connectors, choose products that are listed and labeled by a recognized testing laboratory such as Underwriters Laboratories or Intertech. These products have been tested to meet safety standards and are suitable for use in electrical installations. Using unlisted or unlabeled products can pose a safety risk and may violate local electrical codes. When installing the new cable, ensure that it is properly supported and protected from physical damage. Use cable staples or straps to secure the cable to the building structure, and avoid running the cable in areas where it could be easily damaged. Also, be sure to follow all applicable electrical codes and regulations when installing the cable and making connections. In summary, several factors can contribute to the problem of a fluorescent light requiring a static shock to start. These factors include insufficient power due to undersized wiring, loose connections, aging ballast, and dirty lamp contacts. To resolve the problem, it is recommended to replace the flexible cable with a properly sized cable, check and clean all connections, consider upgrading the ballast, and clean the lamp contacts. By addressing these issues, the fluorescent light should start reliably without the need for static electricity discharge. And finally, it is always recommended to consult with a qualified electrician if you are not comfortable performing the work yourself or if the problem persists after making the recommended repairs. The National Electrical Code, or NEC, is a comprehensive set of standards and guidelines for electrical installations in the United States. It is published by the National Fire Protection Association, or NFPA, and is updated every 3 years. The NEC covers a wide range of topics, including wiring methods, overcurrent protection, grounding, and equipment installation. The NEC is adopted by many state and local jurisdictions, and compliance with the NEC is often required by law. When working with electrical installations, it is essential to be familiar with the NEC and to follow its requirements to ensure safety and compliance. The NEC provides specific requirements for wire sizes based on the ampacity of the circuit. The ampacity is the maximum amount of current that a wire can safely carry without overheating. The NEC also provides requirements for overcurrent protection, which is designed to protect the wiring from damage in the event of a short circuit or overload. Overcurrent protection devices, such as circuit breakers and fuses, are sized to protect the wiring based on its ampacity. The NEC also includes requirements for grounding, which is designed to provide a safe path for fault current to return to the source. Grounding helps to prevent electric shock and reduce the risk of fire. The NEC also covers the installation of various types of electrical equipment, such as lighting fixtures, receptacles, and appliances. The NEC provides specific requirements for the installation of each type of equipment to ensure that it is installed safely and correctly. In addition to the NEC, there may be other applicable codes and regulations, such as state and local building codes. It is important to be familiar with all applicable codes and regulations before performing any electrical work. When in doubt, consult with a qualified electrician or electrical inspector to ensure that the work is done correctly and safely. Principles of electricity are governed by several fundamental laws and concepts. One of the most important of these is Ohm's law, which describes the relationship between voltage, current, and resistance. Ohm's law states that voltage equals current times resistance, or volts equals amps x ohms. Ohm's law can be used to calculate the voltage drop in a wire, as well as the current flowing through a circuit. Another important concept is power, which is the rate at which energy is transferred. Power is measured in watts, and it is equal to voltage times current, or watts equals volts x amps. Power is used to calculate the energy consumption of electrical devices, such as lighting fixtures and appliances. The electrical circuits can be either series or parallel. In a series circuit, the components are connected end to end, so the current flows through each component in turn. In a parallel circuit, the components are connected side by side, so the current has multiple paths to flow. The voltage is the same across each component in a parallel circuit, while the current is the same through each component in a series circuit. Electrical circuits can also be alternating current, or AC, or direct current, or DC. In an AC circuit, the current flows back and forth, while in a DC circuit, the current flows in one direction only. Most household electrical circuits are AC circuits, while batteries and some electronic devices use DC circuits. When working with electrical circuits, it is important to understand these basic principles and to follow proper safety precautions to avoid the risk of electric shock or fire.